Okay, so good afternoon, everyone. Sorry for a bit of a setup delay. Um, just to make sure, is my sound coming okay? Anyone cares to respond? Great, terrific, thank you. Okay, so the plan for today is we are going to look at probabilistic models for dealing with temporal data. And that's a theme we'll also continue on Thursday. So we'll go through a couple of important sort of methods for that. But before I do that, I want to wrap up what we were discussing last time. So just by way of recap, towards the end, I had described these naive Bayes classifiers, which is something I'm sure most of you have seen before, but kind of very loosely speaking, the idea is that different features of the sensor data that we are observing, we kind of assume that these features are independent of each other. And what that lets us do is simplify the Bayes rule that we use to make the inferences. So kind of the idea is that if we knew the joint distribution between the features and whatever inference we are seeking, then I can always ask all sort of queries. And in particular, I can ask that given the sensor measurement, what was the most likely state that the inference, the state that we are trying to infer. So like, for example, the state of a human being or of a plane or whatnot, right? So that hidden state. And what this assumption about independence lets us do is to really get away with a lot fewer data. So in one of the challenges with in a lot of systems is that our ability to collect label data are limited. As I mentioned a couple of times in the course, unlike, let's say, images and all, where you can farm out images and ask random people to label them and make use of that data. With sensor data, the problem is that only the person wearing the sensor probably has easy access to what the ground truth was. So label data tends to be costly, trickier in this setting. And the reason we are able to get away with less data is that if I have, in this example, let's say D features, then there are, and let's say these are all binary variables, then you have 2 to the power D possible states, right? So you would need data for each one of those bins. On the other hand, if we have made the assumption that these are independent, then we are left with 2D bins. So instead of exponential number of bins, we have linear number, and that's what simplifies things. And then once given this assumption, then you can, it's basically a matter of counting in your training data how to get these different probability distributions, right? So for get the parameters for the probability distribution. So for example, in this case, given different possible combinations of sensor input, what the hidden state Y was. So it's just a matter of counting. So we had gone through that. And then I'd also talked about that how we can generalize this thing to the case where your features are continuous. And kind of the idea is that now we basically begin to say that these features are Gaussian. And then basically we have to deal with mean and variance in that case. And again, rest of the stuff kind of remains the same. So now you use the data to get the parameters of this Gaussian distribution. So very similar, just a generalization of naive Bayes. And finally, towards the very end, I mentioned that one of the challenges is that for many continuous valued things, this reducing to a single normal distribution doesn't work. So this example, let's say the feature was start time of some activity. Oftentimes human activities don't have a single peak. So in this case, it was start time of eating activity, and typically we eat like 3 meals a day. So more likely our distribution would look something to which has 3 peaks, and they're kind of smeared differently. So the generalization becomes mixture of Gaussian models. And kind of the idea is that now we say my continuous variable is really a summation of a certain number of known, certain known number of Gaussian variables. So how many Gaussian variables you have is known. So very common. So you pick some m, and that comes from your domain knowledge. So in this example, the fact that typically we have 3 meals a day. And then the idea is that now you have parameters corresponding to each one of these m normals as well as the weighting function. So in some senses, we have 2 parameters per normal, and then we have the pi m, pi sub m, and together with a constraint on it because the weights have to add up to 1. And at the very end, the last slide I had was this algorithm, where kind of the idea is basically we go through an iterative process where we initialize the parameters of these Gaussians, and then we kind of go ping pong between 2 steps. So in first case, what we do is we update the parameters given the current data assignment, and then we change the data assignment. So what we do is we take the points in our training set and we move them towards the nearest Gaussian, and we kind of ping pong between them until the process converges. So this is called as expectation maximization algorithm. Pretty simple. It's a category of algorithms which are iterative in nature, and very loosely speaking, what's happening is we start with an assumed set of values for the parameters, and then we update the training set according to it, and then we recompute the parameters, and we go back and forth until we converge. Okay, so that's these naive Bayes Gaussian mixture. They're pretty useful in the sense that particularly in settings where you don't have a lot of data, they actually do pretty well. And in fact, if you use very more powerful models like neural networks and all arbitrarily, and you don't have enough data to train them, you will end up with a situation where your model will artificially do very well on the training data, but then when you take it to an unseen setting, then it won't generalize well. So there's a huge degradation. So one of the challenges is always that you got to make sure that your whatever model you're coming up with works more generally. Okay. There are other classical classifiers which sort of are commonly available and used. Decision tree and things based around it, very loosely speaking. This is how we humans do classification, right? We look at some features, and some expert will tell us various thresholds, and also in this particular case, like for example, for different kind of activities, we might look at the count of events in different sensors and what was the time of day and things like that. So this is just some sort of made up example, but the idea is that the parameters in this particular case are the threshold values which are making our different decisions. And the process of training really is a process of coming up with those parameters. Very common is to have an ensemble of decision trees, so like a whole bunch of decision trees, and then you vote across them or weigh their decision. So these kind of approaches are referred to forest, so a forest of trees. I'm not going to go in depth in there, but these are usually available easily as functions to call in packages like scikit and all. And the final one, which is probably the one which most commonly gets used because it again does pretty well, is support vector machines. And kind of the concept out here is as follows, that I have 2 classes. So kind of the one which are shown with filled dots and the one which are white dots, right? So they represent 2 different activities, in this case, hand washing and sweeping. And kind of the idea is that we want to find these things reside in some n-dimensional space, right now in 2 dimensions. And the idea is we want to come up with a hyperplane, in this case, a line, which divides the 2 classes. And if we are lucky, our classes may be such that we can indeed come up with a line like this. So that line is what is shown out here, this guy, the black line. And intuitively, the idea is that we want to find that line such that it's what is called as margin, which is the distance between from the line to the nearest point in the sweeping category and the nearest point in the hand washing category is equal, right? So we want this boundary to be exactly halfway through. So you can imagine that I can have many different lines with many different slopes and intercepts, but there would be one such line which divides things equally. Okay, so that the margin of error that we have is equal. And in essence, this problem boils down to is minimize. So if this W, the weight vector, which takes the feature input X, and then B is the intercept. It turns out that this margin really depends upon this W. So this boils down to an optimization problem where you are minimizing W, or actually the way it gets formulated is that you, for a variety of mathematical reasons, is that you are minimizing half of W, the norm of W, such that this constraint is met. Actually, what this constraint is really saying is that we don't have any error. Okay, that is, or if yi is 0, then I'm on one side of the line, and if yi is if yi is 1 or -1, depending upon that, you are on one side or the other. So the idea is that y is negative or positive, and this is ensuring that. So this is a good case. Now, the problem that we often run into is that oftentimes our data is such that you cannot find such a line. So the setting that we have is, and that's more typical of real life, is that there are some points. So like in this case, some hand washing points are sitting on one side and some sweeping point might be sitting on the other side. And so a separable line or a separable hyperplane is impossible. And in that case, what we do is we allow for some error. So kind of the idea is we would like to find a hyperplane which divides things as cleanly as possible, but recognizing the fact that we may have some points which may be on the wrong side. So what we do is we allow for a error margin, and that is represented by this Greek symbol. And what we're basically saying is for this error for every such point is also now part of my minimization objective. So we basically retain our notion of margin, but we allow for the fact that we have a bit of a soft error. And that is why this error terms kind of creeps in out here. And then these error terms all have to be greater than 0 because it's on the wrong side. So so this is the full-blown version of support vector machine. Now, so besides, so one situation we have out here, like I said, is that such a plane may not be possible. But oftentimes what happens is in this higher dimensional space, maybe a plane is not possible, but maybe some other shape is possible. Maybe it's a situation that all points are clustered, like something like in a two-dimensional space. You might imagine that one activity is out here, and then all the points outside are a different activity. So while a line is not possible or a plane is not possible, but maybe some other shape, in this case, a circle is possible. So oftentimes we are in a non-linear situation. And if you know something about the domain, maybe again, you could make use of it. So one thing which is often commonly done is that instead of operating in my original feature space X, what we do is we go from that feature space X to some nonlinear space. So we kind of subject our features to a nonlinear transform. So for example, I could do a radial transform or a whole bunch of other things, and that might give better results. So what is often done, therefore, is this form of nonlinear support vector machine where we map our, we make use of these nonlinear kernels in order to see that maybe there is an underlying structure, so that while a linear plane may not exist, but a non-linear one does. So we basically transform our input space. So there's common nonlinear kernels that we would try out and see if they lead to a better result. So that's SVM. I'm not going to spend much time on that either. And part of the reason is that all of these methods that we have seen thus far, right? Support vector machine and decision tree and all, they really are kind of mostly designed for static cases. They don't really have a notion of time. Now, you could apply them to time still. So what you could do is, let's say I'm applying support vector machine. So what I can do is I can take my features to include the current measurement, and let's say the measurement in the preceding time step and the measurement in the time step before that. So I can take a window of samples and I can take all of them and think of them as my feature, right? I mean, so now the challenge there is that if you were to do it, right? So let's say you're trying to predict the location of a robot at the next time step, right? So you have the location right now, the location whatever sensor measurement right now, and the sensor measurement previously, and the one before that, and the one before that. You could take all of these in order to predict the current location. So that way you have a history of measurements. The problem, though, is that we still don't have a notion of time, right? Because unless we also take into account what time they were in, like a particular sequence. Now, the challenge out here is that the features that we are using thus far in decision tree and naive Bayes and all, there is no sequence among them. All features are equally important, right? It's almost like I have a set of features as opposed to a sequence of features. So I've lost. So even though you could take a sequence of measurements and feed it into an SVM, but you have lost the fact that they were a sequence, because SVM just thinks of them as a set of features. Now, you could attempt to kludge your way around it. Like, for example, you can say you could begin to create tuples of like the value and how much time in the past they were. So I can say current measurement has some value and its time offset is 0. The measurement which came before that has some value and it has an associated time step, and so on and so forth. But again, it's not clear how you could really make clean use of it. So all these methods that we have, basically the issue is no notion of time. So and like I had laid out as the goal earlier on in this course, that we're really looking at these kind of sensing and control systems. So we're interested not simply kind of at a snapshot, but really over and somehow we need to capture that notion of time. So the methods we are going to focus now on are the one where time plays an important role. By the way, in this category of methods which ignore time is also methods from neural networks. So I'm sure many of you have probably seen at least neural networks which work with images, seen in a convolutional neural network of various type. Again, no notion of time. I can feed them a sequence of measurement, but again, the fact that they are a sequence is not accounted for in any particular manner. Okay, so let's look at the temporal models. So dealing with time-oriented data, of course, is not new. So there are classical methods which work with time. So we are going to spend some time on it, some time discussing those before we move to next week on the more recent kind of methods. Okay, so in order to do that, what we are going to do is we're going to spend some time kind of discussing how it is done. So if you might recall, kind of earlier on, I had kind of defined our inference problem in terms of kind of a hidden state and some observations that we are making, and the fact that from observation, we really wanted to know the hidden state. So that was one of the early slides out here. So so again, those of you who have forgotten, just want to, I should have had the slide out here, but let's just revisit that for a moment, so that oh gosh, where was it? Yeah, so that we have a set of so we have a set of states at different time, and we have a set of observations, and our goal basically is that we want to make some inference about as in the slide, that we are given a set of sequence of observation up to some time step n, and what we want to do is we want to basically say that what the activity sequence was under the hood, and we had done various simplifications and all along the way. So now let's revisit this, but this time around we are going to develop methods which keep the notion of time with us. So first thing is that we start to think of these states in a probabilistic manner. So you could say that the state at any given time t is some random variable, and it can take a bunch of values. So let's say I'm trying to figure out, let's say, stress behavior. So the state could take two values, let's say stressed or non-stressed. Or maybe you have a more rich stress model. Maybe it has like 5 levels: no stress, somewhat stressed, all the way to extremely stressed, right? So the state at any given time is taking some a value from a set of values. And then I have the state is evolving over time. So these random variables, in particular random variable s of t, is really telling me what the it corresponds to the state at time t, and that itself takes some values. So if you're thinking of these as random variables, so the idea is that we want to basically say what the state at time t is going to be given all the preceding states since the world started. Now, of course, we know that time is causal, so it's reasonable to say that S of t is independent of that we don't have to worry about the future states, right? So we are only worried about the past. We assume that we know the initial state and when the system started. So first problem we face in this setting is that clearly our history is growing as time is growing. And so as you may have seen in many of your other courses, we in engineering solve this thing by making this Markov assumption, which basically says that we are going to assume that ST depends only on a finite fixed number of previous states. And very commonly, we use the so-called first order model, which basically says that S of t depends only on the preceding state. So if I'm looking at this guy, then all information that is necessary to learn about S of t is captured in the prior one. Okay, so given Si minus 1, I am independent of anything which came before that. Okay, so that's the very common one. Let me ask you the following: if if let's say I were to tell you that S of t depends upon 10 previous states, can you convert it into first order Markov process? So let's say I'm saying ST depends on ST minus 1, ST minus 2, all the way to ST minus 10. And so do you think, is there a way to convert it into so that ST depends only on the preceding state?
We could multiply the probabilities using Bayes theorem.
No. I mean, you'll still have the dependent. I mean, you can multiply, but you will still be dependent on the previous ones. Yeah, so someone else was saying something. Yeah.
You could roll them into another variable of the state and then have like a rolling window of your last 10 states.
Yeah, exactly. So I basically create a kind of, I amplify the state. So I will define a new state vector, new type of state, which is really the preceding 10 states, right? So I just amplified my state vector. So so more complex things. So like in case of second order, what I can do is I can define my new state, and we are going to call that, let's say, X. Okay, this is new state definition, and S is the tuple. X is X of t is the tuple. S of t, S of Yeah, it's the tuple S of t and S of t minus 1. Okay, so I'm just kind of remembering, like you're suggesting, remembering other elements in that window also. So increase, so you could think of it as that I'm augmenting the state. Now, oftentimes this notion of fixed number of state is not simply the recent case state. Like if you were to think of like, I don't know, my activity, or human activity at given point in time, certainly it depends upon what you were doing recently, right? But there are also daily cycles and sort of week of day type cycles and yearly cycles. So you can imagine that maybe it depends upon the recent one or two states, but it also depends upon the state 24 hours ago, roughly, and then the state a week ago, and also perhaps the state a year ago, right? I mean, there's some influences which arise from the way we humans operate. So if you were to look at kind of this dependency graph, that what affects the state at any given point in time, there might be these long distance connections also. So in which case you'll have to keep track of those as part of the state augmentation. But in any event, I mean, the point to remember is that I can reduce, if I know that I'm dependent upon a specific fixed set out of the history, then I can just basically remember it. Of course, my cost of maintaining the state is going up. Okay, so second problem that we have is that we have infinitely many t's, right? And so if for each s of t we had a different distribution, then again we'll be in trouble, right? I mean, I'll have like zillions of infinite number of parameters in my in my model. Parameters in this case are nothing but your probability distribution. So we solve this thing by, again, another classical assumption that I'm sure you have seen in some courses or the others, the stationarity assumption, which basically says that probability distribution of s of t given the history is the same as probability distribution of s of t prime given the history for all values of t and t prime. So essentially, we are saying that the process is following kind of a static model. Okay, so that I only need to maintain a finite set of parameters. So between these two, right? I mean, the Markovian assumption and the stationarity assumption, we are good to go in terms of the state transition. Now, this is only half the story, right? I mean, this is how the world is, right? This is describing the dynamics of the underlying world. If it is continuous time, then it would be some differential equation. If it is discrete time, as we are kind of assuming out here, then it is more of a difference equation kind of thing. But anyway, that's the transition model. But we also need the sensors. So the idea behind the sensors is that given the history of state and the history of observations, we want to say what the probability of the observation at the current time step is, right? So OT, or uppercase O of t, represents the random variable corresponding to the observation right now, right? I mean, so if these were accelerometers on a human body or whatever, radar observing a moving aircraft, whatnot, it is the observation at current point in time. And this is conceptually or intuitively, this would depend upon all the preceding states as well as the preceding observations, but because clearly it's not independent of them. So a good choice again out here is, because this is again going to be hugely complicated. So a very common assumption is another Markov assumption, which we call a sensor Markov assumption. Remember, the previous Markov assumption was about the states. Here it is about the sensor. And we are basically saying that OT, given the history of state and the history of observations, depends only on the current state. Okay, so this is another important thing. We're basically saying what we are observing from the sensors right now is dependent. If we know the current state, then that is enough. Okay, that is, current state is capturing all that needs to be known about those two histories. So that's another assumption we are making. So now, if we were to sort of draw out how these different random variables look, our graph. So this is what is called as a Bayesian network. And I'm sure some of you may have seen Bayesian network, but those of you have not, think of it this way, that I have a bunch of random variables, and I'm really interested in knowing their joint distribution. So in the worst case, we have to say everything has some dependence on each other. But that's not the reality. The world has a lot more structure because of these Markovian assumptions and such. So what these arrows are saying is are capturing this dependence information. You can intuitively think of it as that if I'm looking at, let's say, ST, then we are saying OT, the OT given ST is the same as OT given everything else, right? So given ST, OT is independent of everything, anything ST dependent upon, right? So if I know the parent of a node or parents of a node, in this example, so then I don't need to worry about the ancestors there. So our two Markovian assumptions are basically saying ST depends only on ST minus 1 and ST minus 1 only on ST minus 2 and so on and so forth. And also they're saying OT depends only on ST and OT minus 1 depends only on ST minus 1. Another way of thinking about it is that these edges are really corresponding to a conditional probability distribution. This is basically saying that so let's say my sensor is a binary sensor. So OT can have values 0 or 1, right? And ST is, let's say, a tertiary state. Okay, maybe it can be sitting, running, and walking. Okay, then my sensor, the conditional probability would be all possible combination, right? So for every given value of ST, which are 3 in our case, I will need to know what the distribution of the two possible values, what's the distribution of O of t, which means I need to know probability OT equal to 0 given I'm walking, probability OT equal to 0 given I was running, and so on and so forth. Okay, so it's basically these edges really basically specify a conditional probability distribution. Now, this type of Bayesian network I'm going to talk. I'm going to describe that a little bit more in detail. But this type of Bayesian network is called dynamic because we have these time slices, right? So this is time step t minus 2, t minus 1, t, and so on and so forth. So it's dynamic because it's time. But Bayesian network more generally are not necessarily about variables which are indexed by time. But in case they are indexed by time in this particular, then they're called dynamic Bayesian network. They don't need to be Markovian and all, but as long as they're indexed by time. So, so Bayesian network and dynamic Bayesian network. Now, what Bayesian network theory allows us to do, and I'm going to dive into it a little bit more, is that given such a graph and given these probability distributions, I can come up with the joint distribution, right? So let's say I'm at time t. Okay, let's say I'm at this time. Then what I'm really interested, we have all the state variables 0 to t, and we have all the observations O1 to OT. Then we are basically saying that this joint distribution between these two t plus 1 variables can be obtained in the following manner. And this is the general way Bayesian network works. What we do is we consider, so this goes to your conditional probability distribution, right? So let's say if I were to give you, so just digressing a little bit, let's say I give you p, x, y, z, and now I say, so I can decompose it into p of x given y, z, probability y comma z, and then I can further decompose it into px given y comma z times p y given z times p of y. So I can always kind of do this kind of a decomposition. So what it translates in this particular case is, so remember, S0 has no parent. So that appears as is. So it's almost like I'm giving you kind of a recipe at this point. And then for every edge, what you are going to have are probability of O I given Si, and then probability of Si given Si minus 1, and you're going to have the product of these, right? Because the only conditional probabilities that would appear out here are the one which are corresponding to these edges. So what this product is doing is accounting for every such edge. So it's accounting for this edge, this edge, this edge, this edge, this edge, all such edges, right? So there are 2t such edges, and that's what is appearing out here. So I'm going to give you an example of why this works, but the idea behind Bayesian network is that given such a structured graph, you essentially, instead of computing the joint probability the kind of the hard way, you basically exploit the structure with a lot simpler factors. Remember, our original formula, P, X, Y, Z, the analog out here would have 2t plus 1 variables. So it would be P, a joint distribution over 2t plus 1 variables. And if I were to do it this way, it would be horrendously hard, right? I mean, lots and lots of terms, right? And I'm not exploiting the structure in any way. This way, once you have the graph, you can exploit the structure very easily by just basically following the arrows. So the joint distribution basically is the product of all the conditional probabilities together with the probability of nodes which have no ancestors. And then kind of the idea is, once I have the joint distribution, then I can ask various kind of questions. I can basically say, given values of some of those random variables, what is the distribution of the other ones, right? In particular, I can say, given values of given these distributions and given probability S0 and some observations, I can say what the value of a particular state is. We'll see some examples of it, but once you have joint distribution, you basically have full knowledge of the system, and you can ask all sort of questions out there. Now, this Bayesian network is a bit of a digression. So firstly, perhaps most of you know about it, but it came out of UCLA in 1980s. Professor Udia Pearl, and this is what fetched him the Turing Award, which is kind of like the Nobel Prize in computing. Okay, actually, just as a digression, what other famous things do you think have come out of UCLA engineering? Anyone?
The internet was started here.
Okay, internet. So that's Professor Len Kleinrock. So the first node on the internet was right here at UCLA. Okay, that's great. What else? Okay, so just in case of bragging rights and stuff like that, couple of other things which at least, well, three things that I know of, and I'm sure there are probably others that I don't. So one is something called Viterbi algorithm. I'm sure some of you may have seen it in your communication courses, but it's really a more general thing, and we'll actually see it in this lecture also, because it's really a general way of making an inference. And it was done by Andrew Viterbi when he was a faculty here at UCLA, okay, before he moved on to create a company, which is now called Qualcomm. Okay, so Viterbi algorithm. Another one is out of, I think, probably our civil engineering department. It's called reverse osmosis. So reverse osmosis is the way to basically purify water, remove impurities. Okay, so until very recently, basically, it has been the only sort of the most cost-effective way, and all you use it in water filters and stuff like that. Okay, so reverse osmosis. Okay, the key thing, major patent out of UCLA, which sort of did that. So that's another one. And the third one was UCLA was a place where the first CMOS radios were made. So you might say, what's the big deal? So CMOS is the semiconductor technology out of which we normally make your microprocessors and all. So it's really very scalable and all. And before, I would say, late 80s, early 90s, people really didn't know how to make radios using CMOS technology because it was not optimized for, people hadn't figured out how to get it to work with high frequencies, which is what radios need. So we knew how to do digital circuits, but not very well how to do RF out of it. So again, the first CMOS radio came out of UCLA, this Professor Asad Abedi and Henry Samueli and sort of that whole group out here. Some of those people are still on the faculty. That led to Broadcom, the company which sort of came out with the first commercial chip. And of course, I mean, now other companies have it, and now you can even put radios on the same chip as the processor. So these are some examples. If any of you ever find something else that has come out of UCLA, which is cool, drop me a note. I like to keep track of these. But anyway, back out here, Turing award-winning thing is called Bayesian network. So the fact that given the joint distribution, I can of a system, joint distribution, so I can describe the system in terms of a bunch of random variables and have a joint distribution of it. I mean, that of course people knew in statistics. What Professor Pearl's main contribution was that this particular computationally very efficient way of specifying this joint distribution. So what this Bayesian network is, it's a probabilistic graph model, okay? And that's a very powerful class of models that machine learning use. There are entire books around it even now. I mean, this is a class of models, and it's great at dealing with uncertainty. Okay, so the idea is that we represent the world as a set of variables and the dependencies among them. And very critically, we say that these dependencies form a DAG, a directed acyclic graph. Okay, so kind of the idea is that the structure of this graph you can maybe figure out from the data or maybe from interviewing experts and all, right? I mean, you can say, okay, what does stress depend on? Okay, well, it depends on heart rate variability, and it depends upon maybe what you ate or your age or stuff like that, right? Your work. So into it, and then you can say, oh, and what does that depend upon, right? I mean, so there is a so you'll have a set of variables, and then there is some dependency structure across them. And what this is saying is that the conditional dependencies, which is given a value, what is the distribution of another variable, is captured as a DAG. So nodes here represent variables which are of interest in my system. There could be sensor observations, there could be hidden variables, there could be unknown parameters, right? I mean, anything which you can reasonably well think of as a random variable would be there. A variable which is fixed value is basically a trivial random variable, okay? Edges represent conditional dependencies. So basically it is saying that if two nodes are not connected, that is, there is not a path which goes from node A to node B, then we are basically going to say that, then what that basically means is that these nodes are conditionally independent. So let's say I have something, well, in this case, right? So I have rain, sprinkler, and grass wet. Okay, so rain, sprinkler, and grass wet are three random variables, and what we are saying is that they have some values. So in this case, they're all binary. Rain is true, false. Sprinkler is true, false, and grass wet is true, false. In this particular case, there is no way to there is well, this is kind of a bad example. Yeah, okay, this is a bad example. Let's say I had this kind of structure: A, B, C. Then it's basically saying that if I know B, then C is independent of A, right? So that's the meaning out here, that nodes okay, and moreover, let's say I have let's say I have this thing, D. Then we basically say that C and D are conditionally independent given A. Okay, so basically the graph structure is used to capture dependence and independence in a statistical sense. So each node has a probability function, and normally if I were to consider the probability function of a node, then I would have to condition upon everything else in the world, right? I mean, if I'm doing the probability function of sprinkler, I would, and since my world has 3 variables, I would have to come up with sprinkler given all possible 4 values of rain and grass wet. But what this edge structure lets us do is we basically only have to worry about our parents. So for sprinkler, we will only have to worry about a table which basically given 2 different values of rain, true and false, what the probabilities are for the sprinkler being on or off. So in this particular case, it's saying if rain is not there, then the sprinkler being on has probability 0.4 and sprinkler being off is probability 0.6, adds up to 1. And if on the other hand, rain is true, then sprinkler being on is close to 0 and sprinkler being on is 0.99. Is presumably one of those fancy sort of rain aware sprinklers, which if it is raining is not going to come on, but it has some potential error. Okay. In case of rain, since it has no parent, so then we are basically just going to go with the distribution independent of anything, right? I mean, so this is the marginal distribution where we don't care about the others. So probability of rain versus not is presumably going to come from, again, from your data, right? In some other cases, it might be some expert providing for other kind of things. And then for grass wet, we have 2 parents, rain and sprinkler. So I'll have to consider all those 4 cases. So those 4 cases, and again, grass. So each row should add to 1. Okay, each row should add up to 1. So now, given this Bayesian net, the joint distribution of those 3 variables, P, G, S, R, we just follow the structure of the graph. So what the edges are. So for grass, we have 2 parents. So we say probability of grass given S and R, sprinkler and rain. For sprinkler, we have 1 parent, probability of sprinkler given rain. And for rain, we have no parent, so there's probability of R. So very easy. So the joint distribution is really a product of K terms if I have K nodes. And then given this, I can ask all kind of questions about it, because I do have the 3, given this and given the 3 probability tables, I can ask all kind of questions. So like, for example, I can ask, what is the probability that it is raining if the grass was wet? Okay, so I can ask this kind of a question, and then at that point it is really applying Bayes rule creatively, right? I mean, I can always go back to kind of the full joint distribution and divide it with some relevant terms. So that's what Bayesian network is. It's a very powerful way of expressing what's happening in the world and these probabilistic terms. And there's a lot of philosophical material around Bayes nets. Does it capture all sort of uncertainty or not? Does it? Do we need more powerful models? Stuff like that. It turns out that actually, basically, it's a very powerful way. Pretty much suffices for capturing uncertainty, and moreover, it begins to let you do thought experiments, in the sense that you can say, what if I had done this? What would have been the impact, right? So it's something which is currently in vogue quite a bit, called causal reasoning, right? Because Bayes nets are capturing cause and effect kind of things also. pertinent to our purpose, we are dealing with these random variables, which we have specifically designed to capture what we are of interest. That is, there is a latent state of the world, and then there are observations that my sensors are making. And at each time step, I have two random variables, and through our Markovian assumption, as well as stationarity assumption, we have basically reduced the problem to to this kind of a graph, where we have conditional probability distribution for each OT, and then we are basically saying that the conditional probability of ST is only depends upon ST minus 1, and by the way, it's the same distribution here as it is here or as it is anywhere else. Okay, so I just need one distribution there. Any questions out here on the model itself? Okay, so our Markovian assumptions are really captured in the structure of the graph, and we are able to get the joint distribution. Okay, so now, given this graph, we can ask all sort of interesting questions. And they basically fall into 4 categories. They're called filtering, forecasting, or sometimes prediction, but I like to avoid the term prediction because it's used a little bit differently in machine learning nowadays. Smoothing, and most likely explanation. So filtering basically says that given the past, and we'll always assume that we know the initial state, right? So this is always implied. S0 is the random variable S0 had the value, small case S0. Okay, so we are basically saying that given the history of observations, what is my current state? Okay, so that's what we are interested in, and that problem is called filtering. Now, of course, we want to do this thing efficiently and all, not because my history is ever growing. Hopefully, we can do some simplifications that we don't have to keep track of the entire history and so on and so forth. But that's the problem itself, right? Given the observations since we started sensing, and knowing the state just before we started sensing, could I say something about what could I give you the distribution? And once I have the distribution, then I can tell you most likely value and so on and so forth, right? I can give you the probability distribution. Then what about of that current state? Forecasting. Forecasting is kind of a variant of it. It basically says, given 0 to t, maybe I'm interested in this value. So this is filtering. This is forecasting. Like I said, forecasting is often also called as prediction, but unfortunately, not unfortunately, but what has begun to happen is that anytime you are coming up the value, you are coming up with trying to say what the value of an unknown is, that itself is now called prediction. So by that definition, even filtering is prediction of S of t. So I'm avoiding the term prediction at all to the extent possible here, but so just bearing in mind that if you read the literature in many places, including the book I'm using, this reference, they, instead of calling it forecasting, they call it prediction, but I want to avoid confusion with the other use of prediction. So prediction is very useful, forecasting is very useful for purposes of control, right? I mean, if you are only going to say where I am right now and make the decision based upon that, that's not very useful. It would, for better decision making, if you can say something about where things are going to be, then I would do it. So like, for example, maybe you're designing a system which is going to intercept an incoming missile, or maybe you're controlling an autonomous vehicle and you want to avoid intercepting with that pedestrian that you saw, that the sensors have seen on the road, right? You want to avoid the pedestrian. So in these cases, to leave you with enough time and to make actions which are safer or more accurate, as the case may be, you want to make sure you want to make some forecast about where that evolving thing, missile or pedestrian might be. Okay, so that's why forecasting is useful. Now, smoothing. So the issue with filtering alone is that I'm only depending upon past observations or recent, current and past observation. But I'm sure you would intuitively agree that my next observation is also telling me something about this, right? I mean, if I'm measuring location at some snapshots, and let's say you have location at 2 p.m. And before, observation about location at 2 p.m. and before, then the observation at 1 minute past 2, of course, is telling me something about where I was at 2, right? I mean, it's not independent. So remember, it's conditionally independent given the state, but it's not independent. So it would be good if I were to take history into, future also into account, not just history. Now, in many settings, that's great. What you have done is you have logged the sensor measurements, and then you have gone back to the lab, and your goal was, given O1 through ON, I want to find out S1 through SN, okay? In that case, you are in a purely offline setting, in which case you have the entire history of sensor observations. And to make a prediction about S1, you can make use of not just O1, but also O2, O3, all the way to ON, and so on and so forth. So it can help make you better estimates of that value. So smoothing is generally, and therefore refers to the problem that I want to make a I want to predict ST prime, or come up with the distribution of that. I want the probability distribution of that, given history from 1 to t, where t prime is less than t. Okay, so we are basically saying I'm willing to take future into account from t prime through t. Now, I described the offline setting, but this could also be useful in an online setting. So let's say you are tracking moving car, okay, and your sensors are giving you observations every 10 milliseconds. And let's say you are perfectly fine that you know the location, the delay in the location of 100 milliseconds is fine. Then that means you can have 10 more sensor samples and then go back and have a better estimate of the location, right? So there is a certain lag you can build in and that you can exploit to make a better prediction of the state at a given time, right? Because I'm telling you that my system only needs to know, the system specification is that I need to know where the car was at 2 p.m. And as long as you tell me 100 milliseconds after 2 p.m., it's okay. And since your sensor was sampling at 10 milliseconds, so you can make use of some additional readings. So it just leads to a better estimate. So it can be used in an online setting where you allow for a certain finite amount of lag. And finally, in many cases, and in particular, things like speech recognition is where that offline version of the problem comes in, which is I give you the history, and then I ask you what was the most likely explanation. So there's a subtle difference. In smoothing, I'm interested in the probability distribution of a particular past state. Here, I'm saying which values of S1 through ST is the most likely explanation. That is, it will give me has the highest probability for this conditional distribution. So in case of speech, for example, it would basically say, given what your microphones received, can you now tell me what was the most likely sequence of words that was uttered? Or in case of activity recognition, given what the accelerometer saw, can you tell me what was the most likely sequence of states? Okay. Whereas smoothing would say that given what you had, can you tell me what the distribution of the state at time t equal to 2 was, right? So that's smoothing. Okay, let me ask you the following. So let's say I give you let's say I give you observation from time step 1 through 10. And I am asking you what was the most likely sequence for S1 through S10. Can I solve it by calculating what which value of S1 gives highest probability for this conditional probability, and likewise for S2 and likewise for S3, and then basically find the most likely value of S1 and then the most likely value of S2 and the most likely value of S3 and say, this is my most likely explanation? So let me say it again. So I gave you sensor measurement from 10 time steps, and I'm interested in finding out what was the most likely sequence of states from time step 1 through 10, A1, A2, A3, right? What was the most likely sequence? Is this problem the same as saying what was the most likely A1? And then separately finding what's the most likely A2, and then finding most likely A3, and finding most likely A4, and so on and so forth, and then give that sequence. So is the most likely sequence the same as the sequence of most likely states? Anyone with intuition either way? So I guess firstly, your answer should be no, they are not the same, because if they were to be the same, then I will not have a fourth problem, right? I mean, if the fourth problem is nothing but smoothing done t times, then there would be nothing interesting about it, right? So trivially speaking, therefore, just from the slide, your answer should be no, it's different. Now, why is it different? Kind of the issue out here is the following, that if I'm looking at most likely state independently, then it could be that let's just consider a pair S2 and S3. So it could be that the most likely value of S2 is, let's say, X, I don't know, let's say it's 10, and second most likely value is 9. And let's say for S3, 9 is S3, 10 is S3 also, let's say, for SC, let's say 4 is very likely, and 3 is the next one. Now, what may very easily happen is that if I begin to look at the pair, the joint distribution, it could be that 10,4 is actually less likely than, in our example, 9,3, because joint distribution could be entirely different. So most likely sequence is not the same as the concatenation of most likely values for individual states. So this is a separate problem, and you can't simply solve it by doing smoothing multiple times. So again, recapping this one. So filtering is basically saying, given the sensor observations thus far, what can you say about the distribution of the current value of that hidden state? Forecasting says, given the observations thus far, can you tell me something about a state at a future instant in time? Smoothing says, given the values of state thus far, can you tell me the distribution about some past state? And finally, most likely explanation says, given the sequence of observation, can you tell me what was the most likely sequence of states that would explain the current observation? And therefore, I'm going to pick that. Okay. And speech recognition is a great example, but so are human activity recognition, these kind of things. This is in general kind of useful, where you collect a sequence of observations and then you are going back. Okay, so any questions before I move on? So I'm going to spend some time now on each one of these four on how we do it. Okay. So one other thing I would say is the following, that the preceding stuff that we had done thus far right? I mean, when we were looking at kind of the more classical methods, there we were basically saying that the states are independent of each other, right? So even these arrows didn't exist. Okay, we were basically, our world model was simply observations explain the current state, and that was it. There was no we treated each time step independently. Okay, so now obviously we have a sequence and we have to worry about it. Okay, so okay, before I go to it, now of course we need to learn the probability distributions corresponding to each one of these edges, and that is the transition model and the sensor model, and they can be learned from the observations. So it turns out that from the observations, so a couple of ways, right? I mean, one is you have some data with ground truth, right? I mean, you have actual, you have lots of traces where you are given the state and you know the observation, then you can kind of do it from it. It turns out there are also methods where given only the observation, you can begin to also just a sec, please. Okay, yeah, that given just the observations, you can begin to learn that probability distribution. So there is a learning task as well you can do. Yeah, and kind of intuitively, the idea is that inference that we are doing when we are inferring those states, right, they provide an estimate of what transition actually occurred and what state generated the readings, and then we can use these estimates to update the model. So we kind of, again, a little bit like that expectation maximization process, we basically kind of iterate between this thing. We say, I have a model, we make an inference from it, and then we go back and update the model. But we are not going to spend time on this at all. I'm instead going to focus on the inferencing task. So we'll assume that we have learned the model, we had the data, we had labeled data, and so from labeled data, learning these probability distributions is straightforward. Okay, so filtering. So remember, filtering is given observation from time 1 through t, we want to say what is S of t. So kind of the idea in sort of these inference algorithms that we are going to see is that you don't want to always start from scratch, right? In the preceding time step, I must have computed what was the most likely, what was the distribution of ST minus 1 given observation 1 through t minus 1. And now I am at step t. So it's kind of stupid that I would go all the way and kind of recompute everything. So what you're really looking for is some way of doing things incrementally, or in other words, some sort of a recursive algorithm where given what the work I have done thus far, can I now use it to compute the next one? So essentially what we want to do is we want to come up with some way where I can do what is shown out here. It's basically saying the prediction at time t plus 1 can be done by making use of the distribution I came up at time t together with the new observation that I had at time t plus 1. And of course, I need to come up with what that function f is. Okay, so that's what we want to achieve. And again, this becomes a game of playing with the probability expressions a little bit. So if we look at our prediction problem at time t plus 1, then we can say that this is prediction given two separate things: the history to time t and the observation at time t plus 1. And that we can, using Bayes' rule, we can write it as observation t plus 1 given state t plus 1 and observation 1 through t, and st plus 1 given observation 1t. This is just Bayes' rule. Now this alpha term, when you do Bayes' rule, there is that bottom sigma term which comes up, right? Which in this particular case is going to be probability of if you were to apply the Bayes rule at the denominator, there would have been the term which is probability of O1 colon T and OT plus 1. But the thing is, that's a fixed term. Fixed term for all different values of uppercase S T plus 1. So you can think of it as a normalizing constant. So it's a common trick in Bayes rule where we basically say it is some value alpha because it's fixed. And when I'm going to calculate this for different values of ST plus 1, then they should all add up to 1. So I can say, I can just keep it as an alpha and then at the end sum it up and come up with the value of alpha. So that's a common trick which is used. So so that's the Bayes rule. And then I can make use of the fact that we have Sensor Markov assumption, which basically says that ST plus 1 only depends upon, OT plus 1 only depends upon ST plus 1. So in particular, given ST plus 1, OT plus 1 is independent of the history of observations. So that is why we end up with this term. So OT plus 1 given ST plus 1 and ST plus 1 given the history of observation. And now if you look at it, this is an update term, and the second term, this prediction term, is just a prediction at the preceding time step. So now I have my recursive equation, which is given the prediction at one time step, I can come up with the prediction at the next time step, given the observation at the new time step. So, so now I have my recursive process, and I can call this function f to be some sort of a recursion function, but in this case it's very simple. It is basically taking the preceding prediction and then multiplying it with this term, which of course comes from our probability distribution tables. Everyone clear on it, or any questions? I think I have an example to sort of go over it, but just to make sure that, okay, so if everyone is clear on this, I can do a little bit of further manipulation on this. So this term, the second term, in turn, can be written as a summation over, so I can write it as this, a recursion of this form, where ST plus 1 given ST observation. Remember, this we did not have direct, this was not quite my, hang on a sec. Yeah, okay. So I condition this thing upon ST and then add this term. So again, kind of a Bayes rule kind of thing, and then do some further algebraic manipulation. And now we end up with our end form, which is we have our sensor model, we have our transition model, which is basically saying state T plus 1 given ST, and we have the recursion, which is ST given O1. So this is the preceding, this was the preceding term that we had. So so this gives us kind of our filtering structure, and one can, in fact, what one can do is we can think of this term as like a message which we are sending from one time step to another time step. So if we call this thing as, actually maybe this should be called F. So it's a message which we are computing at time t, and then we are sending it to time t plus 1, and then again at time t plus 1 we compute another message. So this recursion structure can be kind of formally cast as this way, that I'm carrying a message which corresponds to 1 through t plus 1, and that in turn is computed using the message at the preceding time step and the observation at t plus 1, and that becomes the message that I'm computing at t plus 1, and then I'm going to send it to t plus 2, and so on and so forth. So, and then we start out with f1 colon 0 to be the initial probability. So oftentimes these things are cast in this message passing way of doing the computation. So let's look at an example. So what we have is kind of a system. So from the book that I copied it from, their notion is the following, that there's a building, there's a security guard inside the building. This poor guard has no visibility into the outside world. So he's only able to look at the umbrella, whether someone coming in has an umbrella or not. And based upon that, he makes an inference about whether it is raining outside or not. Okay, so there is the rain, which is a random variable, whether it's raining that day. An umbrella basically indicates whether it's a sensor. So you can think of the umbrella being a binary sensor. If the person, so let's say is specifically looking at one person. So if that person brings the umbrella, maybe it's raining outside or whatever, will rain today. And if it doesn't bring an umbrella, then not. So what we have is a sequence of days. We're seeing an extract out here, t minus 1, day number t minus 1, day number t plus 1. Rain and umbrella are the two time indexed variables. Now, in our case, we will need a sensor model and we will need a transition model. So this matrix, this table is telling us the transition model. It is basically saying that if yesterday it was raining, then with 0.7 probability, it will rain today. And if yesterday it was not raining, then with 0.3 probability, it will rain today. In this particular case, because every variable is binary, so we are, and the rows add up to 1, so we are not plotting, we are not drawing, writing down the second column. And our sensor model looks like the following. It basically says, if it is raining, then the probability that the person, our sensor, our umbrella sensor says true is 0.9, and that it doesn't is 0.1. And if it is not raining, then probability that the umbrella would be brought is 0.2, and otherwise is 0.8. Okay, so these are our two conditional probability matrices. And let's say our goal is the following. We have observations U1 and U1 and U2. So we are given two observations, and we want to predict the state of rain on day number 2. So the way we proceed this thing is, on day 0, we know nothing. So our prior belief, and let's say we live in a place where it rains a lot, half the time it rains. Okay, so we'll basically say that probability that it was raining out was 0.5 and it was not raining was 0.5. Of course, it doesn't have to be this way. If you have a different prior, you are going to use that. Day 1, we see an umbrella. So U1 is true. So now what will happen is, using that message passing framework, we are going to compute. First, we are going to compute what the probability of R1 is. So that comes from our transition matrix, right? Because we have PR0 and we have the transition matrix. So now we can develop PR1, and that it turns out to be 0.5, 0.5. So remember, this is the prior belief that I have whether it is raining outside or not. But what we are really interested in is whether it is raining outside or not, given that we saw the umbrella, right? Because umbrella appeared. So now I can do the base game, and you do a little bit of manipulation, and then you end up with this 0.818 and 0.182. And then day 2, again, we saw the umbrella. So now what I can do is, given R1 given U1, I can compute R2 given U1 using the transition matrix. And that gives me this value. And then given that, I can compute R2 given that I saw the umbrella on both the days, and which is what we are really interested in, this guy, right? So I get this vector. So 0.883, so it's basically saying with probability 0.883, it is raining outside on day 2, and 0.117 it is not, given that I saw the umbrella on both days. And so this way we are kind of proceeding from T0 to T1 to T2, and that's the process. And that is what is encapsulated in these equations out here. So it's kind of a recursive algorithm, kind of a lot of bookkeeping and all. And of course, there are packages which just let you work with this. So for discrete valued sensing tasks, using this kind of structure, given that you have the underlying Bayesian network and your associated probability tables, you can sort of work easily. Intuitively, what is happening is, if you notice here, we had said that probability it was raining was, probability that it is raining outside is going up because we are seeing umbrella in 2 consecutive days. You could also imagine, and we'll see it next, that given U1 and U2, maybe I want to compute R1. So the idea is on day 1, I saw the umbrella and I end up with a probability 0.818 that is raining outside. But if day 2 also I saw the umbrella, then I would say, it maybe my belief that it was raining on day 1 is even stronger. So that would be an example of smoothing, going back in time. So, but thus far it is only filtering. That is, given the observations thus far, so on day 2, or given the observations on day 1 and day 2, we are making a prediction of what we are trying to infer what the state of rain is on day 2. Any question on this example? Okay, so let's move on. So that's filtering. The second problem is forecasting. So task of forecasting is really essentially we have no new observations, right? I mean, that's the only difference. So it's almost like I have some missing observations, right? Otherwise it's kind of the same kind of a process, right? I mean, we are moving one step to another step to another step. So in this particular case, what we are really trying to do is we are given, so we are trying to predict the state or infer the state at t plus k plus 1, but we are only given observation 1 through t. So I can break it up much like before in this particular manner, and kind of the idea out here is the following, that for the time period from t plus k onwards, we don't need the sensor model, right? So I would have, using standard filtering that we saw, we can get to S of t, and then after that we use this recursion with no sensor model, and then roll things forward. So it's just an adaptation of the preceding step. And one thing that happens in these systems is the following. So let's say I'm trying to forecast way out in the future, right? So after some time, our observations that we had made, so let's say I've made observation until time step 100, and then I stopped getting any observation. So for a little bit, my observations are still valid. So I didn't get an observation at 101, time step 101. I did the state forecast. Those observations that I made until time step 100 are still relevant, maybe still at 102. But let's say I'm looking at time step 1000. Well, the observations are now way past in the history, and they will probably not have much of an influence. They don't have much relevance. So essentially what happens is that if you forecast way in the future, your forecast will converge to some stable value, which is really reflective of the information about the state given no observation, right? Because observations are so far in the past. So you can intuitively kind of think of it as that from the point I stop getting any observation, and as I'm predicting farther out, then after a while, all these states kind of mix up, and I end up with kind of the prior distribution, that is prior belief that I may have, right? I mean, so in our example, if it rains half the days and doesn't rain half the day, what will happen is that if I stop making observation and look way in the future, I would have to say that, okay, the likelihood that it will rain is 0.5, and or the probability that will rain is 0.5, and the probability it will not rain is 0.5. So there is some sort of a mixing time beyond which our observations that we made are no longer valid. So essentially what it is saying is that any attempt to predict the state way in the future is futile unless your mixing time is also very long, right? I mean, so unless your process, if your process doesn't have slow dynamics, then maybe you are still okay. But if the process is changing rapidly, then after very soon your ability to predict will disappear, and all you can say is what you could say without any observation, namely the prior belief that you have. So that's forecasting. Now, forecasting is something which is, I mean, firstly, one area where people do forecasting a lot is stock market. You have time series data, you have all sort of sensory input, right? State of economy, war, insurrections, and whatever geopolitical developments and stuff like that. But then also in other settings, also it's useful. So like I've given the example of autonomous vehicle, which is trying to avoid hitting pedestrians and other cars. So it would track things and then try to predict their trajectories, forecast their trajectories, so that it can then plan a path which will avoid those, and then it will keep doing it every time step, right? Every time it gets a new measurement, it will again update the forecast about the locations of those potential things on the road. Something very similar on, let's say, guided anti-missile missiles, right? So you're kind of warfare battlefield setting, your radars are tracking an incoming missile, and you have shot the missile which is going to hit it, or whatever, torpedo, which is anti-torpedo torpedo, right? I mean, those kind of things. So there again, you are making observations about that incoming entity and then updating where they are going to be, and you are meanwhile trying to guide your intercepting entity to sort of accordingly. Okay, so in this case, it's exactly the opposite of autonomous vehicle. Here we are actually trying to intercept, whereas in the other case we are trying to avoid. But the purpose is kind of the same in either case. So that's forecasting, and as you can imagine, that for control purposes, it plays a very important role. Okay, so next up is smoothing. So if you recall, the problem in smoothing is that we are given observations up to some time, and we are trying to now find what the state was at some time in the past. And the purpose is that by kind of the intuition is that by taking into account future observations, I can make a better prediction of this state, better inference of the state than I would have otherwise. Okay, so essentially, this is the problem of coming up with the distribution of Sk given observations from 1 to 3, 1 through t, where k is in the past. And here again, you'll see a pattern emerging that we will again make use of a recursive algorithm, except instead of a forward-only recursion, the idea is we will go from state 0 to this forward recursion, and we are going to go from final state backward in a backward recursion, and the two will meet. So otherwise, kind of a very similar concept. And the way it kind of works is the structure is very similar as before. So we have probability Sk given observation 1 through t. So again, I can decompose these observations into two parts. the part which is up to this instant, and then the part which is for the future, right? So past and future. And then using Bayes' rule, I can say that probability Sk given those two chunks is probability Sk given the past, and then probability of future observations given probability of Sk and and observation from the past. Okay, so I can decompose it in this particular manner. Okay, and then from this, I basically make use of, again, conditional independence. So we know observation in the future will only depend upon Sk. Okay, because if I know Sk, then we basically cancel out everything from the past. So there is a this term disappears, and then finally this term is really our forward message from before, and we call this guy, that is OK plus 1 given Sk, as to be the backward message. So and what is happening is that we have these F and B are really vectors, and what is happening is a pointwise multiplication out here. So that's kind of the structure. Let's delve into it a little bit more to see how it sort of breaks down. So what we have now is, let's look at this term, the backward term, because the forward term we already have done previously. So if you look at the backward term, again, we do some manipulations out here. So we can condition it upon Sk plus 1, end up with this term. Finally, you do some algebraic manipulation and you end up with this term, which looks kind of like before. There is a sensor model, there is a recursive term, and then there is a transition model coming in your state transition. Long story short, if you look at the recursive term here, it versus this, it's basically a backward recursion. We are going from k plus 2 to k plus 1. So this computation becomes that we are measuring message at time k plus 1 given the message at time k plus 2, and there is a starting condition which is t plus 1 to t, which is basically just 1. So this looks very much like the forward one, and kind of the basic structure then is again, much like we did the recursion with the umbrella example previously. You can do it out here. So in this particular case, we are doing smoothing, same example, and we are interested in finding what is the probability of rain 1 given we saw umbrella on both the days. I'm not going to walk through this example in more detail, kind of all the details out here, but it's just literally following this. We kind of do, there are two terms, one coming from the left, the other coming from the right, and that lets us estimate things. What I want to point out is that with all of this, we end up with probability of rain 1 given both the observation is 0.883. And if you go back, in this example, the probability of rain 1 given only day 1 observation was 0.818. So what has happened is that our confidence, as a result of smoothing, our confidence that it rained on day 1 increased. So we have a better value. Okay. So this is very useful in a lot of settings. So like, let's say human activity recognition and all, right? I mean, let's say you saw walking, running, walking. Okay, maybe if you were to just go initially, then maybe you had said, okay, maybe it was running, but maybe after you do smoothing, we'll say, okay, instead of running, perhaps it was jogging, or maybe it was still walking. So future observations can correct things, right? So so you can think of it like a little bit like a low pass filtering. We are smoothing things out. So that's why it's called smoothing. So very useful. And if you don't need to, if you can incorporate some amount of future observations before you actually make an inference about the state, then it's always very useful. So so that's the purpose out here. And algorithmically, it basically looks like two loops. One where you do a forward path and another where you do the backward path. Okay, it's basically the algorithm that I mentioned before. Now, one thing that happens is the following, that excuse me, okay, that oftentimes we want to smooth the whole sequence. So what the problem that you may face is the following, that you are not just trying to smooth at one point, but you're trying to smooth at all the points. Okay. And the challenge then is that if you're running the whole algorithm again and again, then there's a lot of work, right? Remember, we are going from left and we're coming from right and meeting in the middle, and then we are again going to do it, but for a different time step. So, so what's happening is that your forward and backward recursion, they were taking constant amount of time per time step. So their complexity is O of t. And if you have to smooth for every time step, then you have t time steps, and each forward backward process is taking time t. So your overall complexity would be OT square. So this is where a class of algorithms that get used are called dynamic programming, which again, I'm sure you may have seen it in some other courses. Viterbi algorithm is actually a particular form of dynamic programming, but kind of the idea is that we remember intermediate results. So this is recursion with remembering. And then the idea is that the complexity, instead of being OT square, goes down to OT. But on the other hand, we increase the memory size. So we basically have to remember things. So intuitively, what happens is we do a forward path where we remember messages at each one of the steps. And then we do a backward path and keep computing the smoothed value at the different time steps. So in the forward path, because we are remembering the values, we need memory to store it. But now the time complexity is one forward path and then one backward path. And so it becomes linear. So that is what this algorithm is doing, which is one forward path and then one backward path. Whereas if you were to do it naively, then for each smoothing point, you are going to go from the left, you come from the right. That takes time, order t, and then you're going to do it for every time step. So this thing avoids it. And the place where we are remembering it is this vector fv, which is basically remembering all the f messages at each time step as we went in the forward path. So we are remembering fv. So that's where we are taking certain amount of space. So so this forward backward algorithm, it basically comes at the cost of space, but it reduces from a quadratic algorithm to a linear algorithm. So oftentimes you are faced with this situation that you have a bunch of data and you are going to be smoothing at multiple points. So you might as well do it this way. So in practice, the problem that this forward backward algorithm has, and we'll see how to sort of get rid of it later on, is that its complexity is how much memory will you need? Well, you need to store the vector f at every time step, and the vector f will have some size, which is really depends upon how many state values you have, right? This is essentially a probability distribution. So it can be pretty memory hungry. So that's one problem. Another one is that usually the smoothing problem that you face is kind of the following variety, that something I mentioned earlier, that my application can tolerate certain amount of delay, let's say 1 second delay. And then what I would say at every time step, I would basically say, tell me what the state was a second ago. Okay, because my application is okay with a second delay and I want high accuracy. So I'm always going to go back in time. So instead of inferring the current state, I'm going to infer the state which my system allows me to, which is 1 second in the past. So what is the most common form of smoothing in practice is what is called as fixed lag smoothing. which is I want to smooth with a fixed known lag, and that specification of the lag comes from my system level specifications. And in that particular case, what will happen is that so what's happening is that I'm getting sensor measurements, right, at different times. I got a measurement out here, and then from that I'm going to smooth things out here. Then I get the next measurement, and I'm going to smooth things at this time step. What's happening is that I'm going to run this forward backward algorithm each time, which is again kind of stupid because I'm going to be doing duplicate work. So in this online setting where we are doing this fixed lag smoothing, you can do things better. In particular, we will see that for HMMs, hidden Markov models, which are a special case of what we have been discussing thus far, we could do this thing in constant time. Okay, so there are efficient versions of doing this process where essentially every time I get a new observation, I basically take just a constant amount of time and update things quite nicely. Okay, so yeah, okay. Let me do the following. We have only 5 minutes remaining, so I'm going to stop at this point because instead of rushing through the most likely sequence. And what we will do is, so what we have seen thus far is kind of this kind of structure where we have an arbitrary Bayesian, dynamic Bayesian network. What we will do is we are going to examine a couple of special cases of it. One is called hidden Markov models, where the states have a particular structure. And we are also going to look at Kalman filters, where the states have continuous values. So those are two special cases. And then we are again going to look at some methods for dynamic Bayesian network. But I'm going to stop at this point. But the key message I want you to take away from this thing is that the class of methods we saw previously ignored time entirely, whereas the methods we are looking at today are making use of the fact that states of the underlying phenomenon, whether it's human beings' activity or the state of the weather or stock price or cars, robots' location or whatnot, they all have some underlying connections to each other. And the kind of models that we are looking at are making use of it, and they avoid, therefore, noisy or outlying inferences that one might otherwise have. Okay, so I'm going to stop out here. I also want to remind you, everyone, that it would be good if you start coming to my office hours in order to discuss the projects. And if the time for the office hours doesn't work, then please reach out to me and we can set some other time. I do realize that some of you may have time zone issues, so we can do things later at night, but so I'm perfectly fine doing impromptu times that you want to discuss, but please do it. I think this week, I just want the conversation to be about, like, you can tell a little bit about any ideas that you might have. I can suggest something. I'm going to send out an email by tomorrow with some project directions from my side. But I also want to listen to sort of any specific things that you might have interest in exploring. Okay, so that's all I had for today. Any other closing questions before I hang up?